Welcome to the next lecture in the series of metal additive manufacturing. Now we have made a part. How do we characterize the part we have made and how do we evaluate the quality of the print will be our prime focus in this lecture. So here we will discuss about mechanical properties. So I have split the lecture into two parts. In the first part, I will try to cover mechanical properties of additive manufacturing printed parts and hardness of additive manufactured printed alloys. I will try to cover the tensile, static strength, fatigue behavior and common defects in additive manufacturing printed alloys in the next lecture. In some materials and process parameter combination, additive manufacture made parts now have mechanical properties which are comparable to that of conventionally made parts. The mechanical properties are comparable. In the lectures series, we have also seen how microstructure can be tweaked so nicely by using additive manufacturing techniques. Porosity affects cracking and mechanical property. So this porosity today is avoided in a big fashion. So this porosity could be because of thermomechanical properties of the metal powder and the laser process parameters. Since the characterization tools have gained lot of importance and the accuracies have strengthened a lot in this characterization techniques, now porosities can be measured easily through non-destructive testing methods. Once you establish the process, you evaluate the part through non-destructive testing ways in order to figure out where there are any porosities present or not. These porosities can be on the surface, in between the inner surface and outer surface, it can be in the inner surface also. So porosity affects cracking because porosity is this. So these porosities affect cracking and it also tries to reduce the mechanical properties. When we talk about porosities, these porosities are not circular in shape, they are random in shape, and when the crack comes, the energy can be diverted or it can lead for further cracking and chipping off. So porosities are very much thought of and it is to be avoided. The density above 99.5% is the first priority for additive manufacturing techniques optimization, 99.5. In the beginning, metal additive manufacturing people were talking about 60%, then they moved to 80, then they went to 90, 95, 98, then 99. Today we are talking about 99.5% densification, especially if the additive manufactured made parts are used in critical mission applications like jet engine components. In jet engine components, there is always a fatigue cycle coming into existence in the service condition. This fatigue cycle can be thermal fatigue or it can be the mechanical fatigue. In addition to the other effects, additive manufactured product density depends on the energy volume given to the material. We saw what is energy volume while discussing about lasers. Inefficient energy flux. What is flux? Flux is nothing but joule per area or power per area. Flux can cause unmelted materials. Unmelted materials can happen because the power is too low or the feed rates can be enormously high. It does not give much time for interacting the laser with the metal powder, resulting in irregular voids and reducing the density. Many a times the irregular volume evolves or pushes smoke. This smoke also tries to get trapped in between the molten portion. So, that also tries to reduce the density. When the laser hits at a powder bed, you can see laser hitting at it, you will have small particles, you will have large particles. So, here you can see not enough power and it is too fast, that is what I said. So, if the feed rates are very high, if the feed rates are very slow, you will have overlaps like this. When the feed rates are very slow, so it is moving in this direction and these are nothing but laser spot overlap. Okay. When the laser feed rates are high, you can try to see this is how the spots will be created. So, you will see jumping and in between you can have layers of metal powders which are not even molten or which has not even melt. So, here you have not enough power and too fast of movement, you can see unmelted powder particles present. These unmelted powder particles, when it is done layer on layer on layer, can get trapped and it occupies a space. Sometimes it occupies a space, sometimes this can be removed while processing and you have two big voids. The next thing is when you use too high power, you can say that inconsistency of melting happens when you use too heavy a power or too high a power. So, you can see here the melt pool will try to move and then what happens, you try very high power. So, the liquid flows and it tries to cover up the particles, and this is a problem when you use too high power. When we use a proper speed and proper power, you will see not any or not many powder particles are present. So, we will always choose a proper power and a speed to get very good quality additive manufactured parts. So, not enough power, not too high power, these two are used. An excessive energy input may cause melt pool dynamics unstable, or instability in melt pool dynamics will be introduced when we use excess energy power, which may enter a keyhole mode that decreases density due to trapped gas pores. Say for example, keyhole something like this, you will see it will try to, and then here this is a keyhole. So, that this is a melt pool and here this is keyhole. So, when we use excess power, it tries to introduce melt pool dynamics instability and it leads to keyhole effect. This keyhole effect leads to gas entrapment in the pores. These spherical pores are likely caused by trapped gases due to melt pool instability and keyhole phenomena. So, like Marangoni effect, you also have something called as keyhole phenomena, which is very common when you do laser matter interaction. The higher densities achievable with additive manufacturing for different materials suggest a discrete optimization guidelines for additive manufactured parameters to achieve optimum volume energy. In order to achieve higher density, different materials suggest a discrete optimization guidelines. The optimization parameters to maximize density by reducing porosity. So, maximization of density. So, from 90 you are moving towards 99.5%. So, when you start moving towards that, so what happens is the pore size will go down or number of pores will go down. by reducing the porosity is done because the pore size and the distribution affect the mechanical property. So, the keyhole effect is brought in because of the melt pool dynamic instability. So, a cross section of the metal additive manufactured part, you can see gas induced porosity. What is gas induced porosity? It is maybe the smoke whatever is getting evolved, or the gas whatever is there is created by the laser movement. So, that gas gets trapped completely in the molten pool. So, that leads to gas induced porosity. So, gas induced porosity to a large extent it will be circular. You can get varying size and varying shape, but predominantly it will be circular. When you try to have process induced porosity, they will have different shapes and size. So, this is basically process induced porosity. This can happen because of shrinkage and the surface tension, viscosity of the liquid did not properly flow and you had something like a keyhole effect which completely trapped these porosities. So, you can have gas induced porosity, you can have process induced porosity. This gas induced porosity can be easily reduced, but this process induced porosity you have to do lot of optimization in the process to develop the required output. When we talk about non-destructive way of evaluating the mechanical properties, we generally start with hardness, tensile strength, static strength and fatigue behavior of additive manufactured alloy. Why is this important? Because in metal additive manufacturing we talk about layer by layer approach. In layer by layer we try to introduce anisotropic behavior. We try to introduce anisotropic behavior. So, this anisotropic behavior, when you put the component for fatigue behavior test, it fails miserably. So, that is why we try to evaluate the metal additive manufactured parts for hardness, tensile strength, static strength and fatigue behavior to evaluate the quality of the output. All these things are part of destructive technique of evaluation. Hardness. Additive manufactured product hardness show mechanical strength. Hardness we directly or indirectly link it up with mechanical strength. The micro hardness of additive manufactured processed alloy follow the Hall pitch relationship. So, as your assignment you are supposed to figure out what is Hall pitch relationship, what is its effect with respect to mechanical behavior. This is an assignment for you. The microstructural coarsening with a large cross section area causing the hardness to drop. So, when the microstructure becomes large, then there is a drop in hardness. So, if the grain size is large, there is a drop in hardness. This microstructure coarsening is due to more thermal input in large area which slowly cools or which slows cooling. So, more thermal input in a large area which slows cooling. Why? Because you are trying to do, as I said, when you optimize the feed rates or when you are trying to do one layer and the second layer, between these two layers if you can have 30% in the new layer and 60% in the next layer or 50-50, then this is what is happening. The microstructure coarsening, the grain will start growing is due to more thermal input in a large area. So, the grain has enough energy, so it starts growing and then which slows cooling. The thermal history of each layer affects the layer hardness. So, from layer to layer to layer there is a difference in hardness behavior which is not a common phenomena in conventional machining. In conventional machining you measure anywhere in the block you will try to have the same hardness. You measure it here, here or here, wherever you measure or here in the back side you will try to get the same hardness. But whereas in additive manufactured parts, since you are doing layer by layer and there is lot of solidification happening on a thin area, you will try to have hardness variation. So, that is what is microstructural coarsening also can happen because of the thermal input. Using different process parameters for the cross section area may improve hardness heterogeneity. Using different process parameter for the cross section area. So, maybe the outer layer is done with a different feed rate, and internal hatching will be done in a different speed rate and power. So, that is what it says, using different process parameters for the cross section area may improve the hardness heterogeneity. Hardness developed in additive manufactured processed ferrous alloy is influenced by process input parameters of additive manufacturing. For multi-layered deposited steel, for example die steel or duplex steel, micro hardness drops from the initial deposited layer and then increases. The micro hardness drops from the initially deposited layer and then increases. So, initially deposited layer micro hardness drops. So, this is distance. So, if you try to talk distance with respect to D, it says the micro hardness drops from the initial deposited layer, and then slowly increases. This happens when previous layer are repeatedly heated and partially annealed. Very important parameter. Repeated heating and partial annealing happens when we do in the additive manufacturing. This inconsistency is due to the liquid melts time dependent cooling rate and the middle area slow solidification rate. Two important phenomena. One is liquid metal time dependent cooling rate, The other one is middle layer slow solidification rate. What are we trying to say? If you have this layer, so here in the center it will be slowly cooling. That is what is said as middle area slow solidification rate and liquid metal time dependent cooling rate. So, here it is cooling rate and here it is solidification rate. So, both things try to dictate the output. That output is nothing but the hardness. Top and bottom additive manufactured parts have higher hardness. Top portion and the bottom portion has higher hardness than the middle portion. So, here you will have lesser hardness, right. So, you will have lesser hardness. If I change this graph and I say this is top, this is middle and this is bottom. So, this is top and this is bottom and you have this is the D, right. So, it will decrease. So, the top and bottom additive manufactured parts have higher hardness than the middle. In low alloy steels such as 41XX series steel, alloying components and carbon affect phase formation and hardness generally happen. So, if you look at low alloyed steel for additive manufacturing, this is AM designed by Porosity. So, you can see here you can have 20 MnCr5 low alloyed steel. So, it has a very high strength and ductility. The gear has very high or very excellent wear resistance. It has inherent toughness in it. It is very easy for machinability and it has no nickel in it. So, it gives a better performance. So, when we try to talk about hardness of additive manufactured or processed ferrous alloys, rapid cooling in additive manufacturing creates hard martensitic phase in high carbon steel, which increases the strength. Rapid cooling, when you do rapid cooling, the C carbon whatever is there, rather than getting dispersed in iron, it tries to segregate or it tries to stay and forms hard martensite. The plain carbon and the low alloy steel are not commonly used in additive manufacturing application due to higher manufacturing cost. Most additive manufactured steels are tool steel with high strength and wear resistance. M2, P20, H13 tool steels are stronger because martensite formed at a lower cooling rate. Martensite is from martensite is nothing but a hard phase. These alloys contain more carbon, which accelerates carbide formation and boosts strength and hardness. So, if you see there, we can compare process. Selective laser melting produced is green one, then LMD produced, laser melt deposition produced is red one, and you can see conventional produced is blue one. At the aging of 480 degrees Celsius, you see there with respect to time almost a very close behavior is there. If you try to compare, it is around about 500 and this is around about 525, 530. So, there is a small variation which is there. So, when you try to do conventional, you see the error bar is very less. When you are trying to do LMD parts or SLM parts, you can see that the error bar is slightly higher. So, we are doing aging at 480 degrees Celsius to get this response. The structure of AM processed tool steel show martensitic matrix with carbides precipitated and austenite. So, this is very important. Martensite matrix with carbon precipitates and austenite is there. Post additive manufacturing heat treatment improves ductility. So, the heat treatment, so it is you are doing annealing. So, improves ductility and toughness through tempered martensite structures with carbide precipitates. So, post additive manufacture heat treatment improves ductility and toughness through tempered martensitic structure with carbide precipitation. Austenitic stainless steel does not have secondary phase or solid state phase transformation. Austenitic stainless steel does not have secondary phase or solid state phase transformation. The finer solidification structure and alloys chemical composition determines strength and hardness. So, it is the finer solidification structure and alloys chemical composition determines the strength and hardness. The hardness of LDED processed austenitic stainless steel as a function of secondary dendritic arm spacing were seen very nicely. The hardness of L laser directed energy deposition process austenitic stainless steel as a function of secondary dendritic arm spacing. So, if you try to see the additive manufactured part, so with respect to Wicker hardness and SDAS, what is SDAS? SDAS is secondary dendritic arm spacing, secondary dendritic arm spacing. Okay. So, secondary dendritic arm spacing which is in microns. With respect to Wicker hardness, you can see the plots which are there. X is SS316, SS316L is this. So, both alloys have identical dendritic structures and chemical composition. A slight difference in carbon content between SL1 316L and 316 affected hardness. You can see the variation, it forms cluster, it beautifully forms cluster, you see. It all forms cluster. So, all these things are SS316L, where the secondary dendritic structure variation you have with respect to Wicker's hardness. Most additive manufacturing aluminum alloys contain silicon. So, it is basically added to the atomized powder, which promotes eutectic solidification. So, this is all eutectic, eutectoid, peritectoid, these all come in the binary phase diagram. So, a basic knowledge about that is important to understand this. Most AM aluminum alloys contain silicon. Why is this silicon? This silicon helps in solidification or silicon helps in flowability, something like that. It has to have some role. So, which promotes eutectic solidification. Compared to other aluminum alloys, eutectic aluminum silicon alloys such as Al12Si and Al Si10Mg have lower AI absorptivity for a wider range of wavelength, allowing AM manufacturing. Lower AI absorptivity. The post-process heat treatment improves precipitation hardened aluminum alloy strength and hardness through finer solidification structures. on post-processing heat treatment improves precipitation hardened aluminum alloys strength and hardness through finer solidification. So, finer structure, the hardness goes higher. Higher cooling rate and alloying elements like silicon promotes finer SDAD, secondary dendritic structure, which increases additive manufacturing alloy hardness. Some post-processing may affect additive manufacture processed aluminum alloy hardness. HIP, hot isostatic pressing, coarsens microstructure and releases the residual stress, reducing product hardness. So, HIP, when you do, it tries to coarsen the microstructure and releases residual stresses, reducing product hardness. This solutionizing and aging can reduce hardness compared to that of as deposited. Solutionizing and aging, these two are very important. Solutionizing and aging can reduce hardness compared to as deposited. This is likely due to solutionizing and aging, which coarsen silicon particles. So, hardness of a additive manufactured part of aluminum alloy, you can see this is SDAS and this is Vickers hardness. So, you have all the stars are AL, this is all AI 4047 and you have the triangles are AI 3SI, box are all, these are all AI SI 10 mg and there is only one, this is AI 12 SI. So, AI 12 SI, so SDAD, these are the Vickers hardness, then it is AL SI 10 mg, these are the things, and then you have AL 4047 which is here, and you can see 4047 they will have somewhere SDAS of 2 microns, then you have AL 3SI which is 6-7 microns, you can have variation. Okay. So, by doing solutionizing and aging can reduce the hardness compared to that of as deposited. This is likely due to solutionizing and aging, which coarsens silicon particles. So, you can do solutionizing and aging on this additive manufactured part. The faster cooling rates in additive manufacturing processed nickel alloys keeps strengthening elements such as molybdenum and niobium in the matrix. Faster cooling rate, almost like quenching. The faster cooling rate in additive manufactured processed nickel alloys keeps strengthening elements such as molybdenum and niobium in the matrix. Point defect cause a great lattice distortion. The point defects, there are point defects, line defects, area defects, volume defects, all these things. The point defects causes a greater lattice distortion, which increases the hardness of AM fabricated samples as compared to that of your cast alloy. Heat treatment transforms IN 625S solid solution strengthened superalloy phases. Heat treatment transforms IN 625S solid solution strengthening superalloy phases. At 700 degrees Celsius, annealing lowers hardness by increasing residual stresses. Annealing between 700 to 900 forms delta, which improves the strength. So, at 700 you do, your hardness reduces and your residual stresses releases. When you do annealing at 800 to 900, it forms del and then you get the improved version. After post processing, AM processed Ti6Al4V has different structural features. After post processing, AM processed Ti6Alv4 have different structural features. Completely there is a change in the structural features. The laser powder bed fusion process processed Ti6Alv4 alloy shows a finer martensitic structure with acicular lath after stress relieving. So, it is finer martensitic structure with acicular lath after stress relieving. Isostatic pressing post processed results in coarse alpha and beta structure. At about 10,000 degrees Celsius, Ti6Al4V alloy changes from BCC beta phase to hexagonal alpha phase and beta phase. So, you see there is a complete change in phase itself when you do annealing or a post processing process. The solid state transformation can result in measurable structures within grain, and alpha phase morphology depends on cooling behavior depending temperature conversions. The solid state transformation can result in measurable structures within grain and alpha phase morphology depending upon the cooling behavior. So, if you look at it, these are the two things. One is Ti6Al4V manufactured by LPBF, and after stress annealing you get this, right, and then this is post annealing by HIP. So, you can see here so how the change in the microstructure there, and this microstructure increases the hardness value. Hardness value it increases just by changing the microstructure, and this is what we studied in our time temperature dependent phenomena, cooling curve, all these things. Some of the post processing treatments such as heat treatment and annealing may release residual stresses and coarsen the alpha phase. Moment the alpha phase coarsens, the hardness decreases, compromising the strength and hardness of the additive manufactured part. The mechanical property increases from precipitation hardening and solid solution strengthening. These two are mechanical property enhancing techniques. Precipitation hardening. So, in the precipitation hardening you get precipitates of carbon which are getting fixed all around the boundary. And the next one is solid solution strengthening is also another way where you can try to increase or decrease with the mechanical properties. So, when we try to have micro hardness plot with respect to the alpha lath width for Ti6Al4V, you can see here this is a spread you get. So, as the lath width increases, you can see Vickers hardness falling down. Smaller or shorter the width, higher the hardness. So, finally, you get a response something like this. The hardness is decreasing with respect to lath width. So, hardness is inversely proportional to lath width. So, points to ponder. Here in this lecture, we looked into list of all mechanical properties of commonly printed alloys. So, what are the commonly printed alloys? You can take iron alloys, you can take titanium alloys, and you can take aluminum alloys. So, here what we do is we compared it with the conventional strength and with the additive manufactured strength. Here nowadays we are trying to get a better mechanical properties as compared to that of conventional strength. There are several parameters. One such parameter we have used till now was hardness. Hardness HV is directly proportional to the grain size. As the grain size increases, the hardness decreases, inversely proportional. Grain size if increases, hardness decreases. So, it is inverse proportion. We studied about it, and we also studied what are all the microstructural changes which happen because of post treatment of AM parts. So, we saw this in this lecture. This is very important. You can try to see for iron, titanium and aluminum alloys, because titanium and aluminum alloys are exhaustively used in automobile industry. Titanium is used exhaustively in aerospace industry and in medical industry it is used, and iron alloys are generally used for heavy engineering applications and for rapid tooling. So, assignments: list some common alloys used in aerospace and automotive industry which can be used in metal additive manufacturing. Try to list down the parts and then try to list down if at all there is any hardening cycle followed for better mechanical properties. Start making these assignments. These assignments need not be submitted to us. It is only for your understanding and learning. Once you start doing all these assignments, you will start appreciating what are all the big changes this additive manufacturing is trying to bring in the community. With that, thank you so much.